Space is not the empty void it appears to be. It is a sea of microscopic dust and gas, an invisible ocean we call the interstellar medium. This cosmic dust is not just space dirt. It is the fundamental ingredient for everything you see in the night sky. By the end of this video, you will understand the incredible journey these tiny particles take to become entire solar systems. How can specks 1,000 times smaller than a grain of sand orchestrate the birth of a star? What hidden forces allow them to build worlds? The answers lie in a story of gravity, chaos, and cosmic construction. What do you think it means that our entire world began as dust drifting in the dark? This cosmic ocean is made of two primary ingredients, with one being overwhelmingly dominant. The vast majority of it, about 99%, is gas. And of that gas, the simplest and oldest elements in the universe make up nearly all of it. Hydrogen, the very first element born from the Big Bang, is the most abundant substance in the cosmos by a staggering margin. Helium, the second lightest element, comes in a distant but still significant second place. Together, these two primordial gases form the invisible, swirling backdrop of the galaxy. They are the bulk material, the main reservoir of mass that will one day collapse to ignite new stars. But if the universe were only hydrogen and helium, there would be no planets like Earth, no mountains, no oceans, and certainly no us. For that, we need the other component, the trace elements that astronomers call metals. Now, in astronomy, a metal is not just iron or gold. It is any element heavier than helium. Carbon, oxygen, silicon, iron, nitrogen, all the atoms that make up the solid world around you, they are all considered metals in this cosmic sense. And they are incredibly rare in the interstellar medium, making up just 1% of its total mass. Yet, without that 1%, the universe would be a very dull place. It is within this precious 1% that we find the true seeds of solar systems, cosmic dust grains. These are not simple specks of space dirt. They are microscopic masterpieces of chemistry, forged in the most violent stellar workshops imaginable. When old, massive stars reach the end of their lives, they do not fade quietly. In their final acts, they become vast cosmic furnaces, fusing atoms together in their cores to create heavier and heavier elements. In their turbulent outer atmospheres, and in the immense explosions we call supernova, these newly minted atoms like silicon, magnesium, and carbon are blasted into space. There, in the cold expanses between stars, these atoms encounter one another and slowly, molecule by molecule, begin to stick together. They form tiny, solid particles. Some are silicates, the same stony minerals that form the bulk of Earth's crust. Others are carbon-based compounds, including graphite and more complex molecules that are the precursors to the chemistry of life. Scientists call these particles refractory, meaning they are tough, stable, and can withstand incredibly high temperatures without vaporizing. This durability is their superpower. They are the hardy survivors, the robust kernels that will persist through the chaos of a star's birth. So while hydrogen and helium provide the overwhelming bulk and the gravitational fuel, it is these rare, complex dust grains, born from the ashes of dead stars, that will ultimately provide the solid foundation for every rock, every asteroid, and every planet in a new solar system. They are the legacy of ancient suns waiting to be reborn. But this raw material needs a workshop, a place where it can gather and begin its work. Scattered across the galaxy, drifting through the spiral arms, are immense, shadowy structures. We see them in telescope images as glowing veils or dark silhouettes against star fields, and we call them nebulae. These are the stellar nurseries. Within their vast, cold interiors, the story of solar system birth truly begins. Gravity is the architect here, but it works slowly over millions of years. It draws the thin gas and precious dust together from the diffuse interstellar medium, gathering it into regions of slightly higher density. Turbulence from ancient supernova and the stellar winds of massive stars helps stir this cosmic soup, creating pockets and filaments where material can pile up. The result is a molecular cloud, a nebula so dense that atoms bind together into molecules, most commonly hydrogen molecules. The conditions inside are unlike anything on Earth. Temperatures plummet to just a few degrees above absolute zero. Near total darkness reigns as the dust within blocks out the light from surrounding stars. And while the density is far higher than the surrounding space, perhaps thousands or even millions of particles per cubic centimeter, it is still a vacuum more perfect than any we could create in a laboratory. You could fly a spaceship through the heart of such a cloud and not even know you were inside it, so tenuous is the material. Yet, by cosmic standards, this is a bustling, crowded metropolis. It is within these frigid, dark incubators that the delicate dance of collapse can finally commence. Here, shielded from disruptive radiation and buffeted by gentle internal motions, those microscopic dust grains become more than just passengers. They become the essential catalyst, the seeds around which a solar system will crystallize. For millions of years, this dark nursery exists in a state of delicate balance. The inward pull of gravity is perfectly countered by the outward push of gas pressure and the faint warmth of the cloud itself. It is a cosmic stalemate, a cloud fragment suspended in time, potentially for longer than our sun has even existed. So what breaks the peace? What cosmic event finally tips the scales and sends the cloud spiraling inward upon itself? The answer lies in a violent intervention from the wider galaxy. One of the most powerful triggers is the death of a neighboring star. When a massive star reaches its end in a supernova explosion, it does not go quietly. The blast sends a titanic shockwave racing through space at millions of kilometers per hour. When this wall of energy slams into a quiescent molecular cloud, it acts like a cosmic fist. The shockwave compresses the cloud's gas and dust, squeezing it violently. In an instant, the careful balance is shattered. The increased density in certain pockets overwhelms the gas pressure, and gravity seizes its opportunity. It is a stellar catastrophe giving birth to a stellar genesis, but a supernova is not the only possible trigger. Our galaxy is a dynamic, spinning structure. As a molecular cloud orbits the galactic center, it can pass through one of the galaxy's spiral arms. These arms are not solid, but regions of denser stars and gas, like traffic jams in the flow of the Milky Way. The increased gravitational pull and pressure as the cloud enters this crowded region can be enough to nudge it into collapse. Sometimes the trigger is even more direct. Two clouds drifting on their own separate paths for eons can collide. Their merger creates chaotic, dense regions where gravity suddenly gains the upper hand. Without one of these external events, a cloud might simply linger, a silent, dark potential for eons. The trigger is the essential first domino. It is the spark that ignites the furnace, the push that starts the avalanche. It transforms a stable, if tenuous, cloud into a collapsing protostellar core, setting in motion a chain of events that will ultimately lead to a shining star and perhaps a family of planets. What does it mean that our own solar system's birth likely required a stellar death or a galactic collision? It means we are connected to the galaxy's most dramatic events, a legacy written in chaos. Gravity finally has its opening, but it does not simply win. There is a precise tipping point, a mathematical threshold that separates a stable cloud from one destined to become a star. This is known as the Jeans Instability, named for the British physicist Sir James Jeans. It is the ultimate rulebook for cosmic collapse. Picture a single, massive fragment within the dark molecular cloud. Two fundamental forces are locked in a standoff within it. On one side, you have the relentless inward pull of its own gravity, the collective weight of all that gas and dust trying to pull everything toward the center. Pushing back is thermal pressure, the energy of motion from the gas particles themselves as they bounce and jostle in the cold. For a long time, these forces are in a shaky equilibrium. The Jeans Instability defines the exact conditions under which that equilibrium breaks forever. It comes down to two critical values, the Jeans mass and the Jeans length. The Jeans mass is the minimum amount of mass a cloud fragment must contain for gravity to overcome its internal pressure. Think of it as a cosmic weight requirement. If the fragment is too light, its gravity is simply too weak, and the gas pressure will keep it puffed up indefinitely. The Jeans length is related. It is the smallest size such a fragment can be while still being susceptible to collapse. A cloud might be massive enough, but if it is too spread out, its gravity is too diluted to pull itself together. This is why the external trigger is so vital. When a supernova shockwave plows through the cloud, it does not just nudge the material, it violently compresses it, packing the same amount of mass into a much smaller volume. In that moment, the local density soars, and according to Jeans's equations, when density increases, the critical Jeans mass actually decreases. The fragment suddenly finds itself far heavier than the new, lower mass threshold required for collapse. It has crossed the point of no return. The thermal pressure, which was once a sufficient defense, is now utterly overwhelmed. From that moment forward, the collapse is inevitable and irreversible. There is no going back, no second chance for equilibrium. The fragment is now committed to a million-year-long fall inward, a gravitational surrender that will light a new sun. This invisible mathematical boundary is the true gatekeeper of star formation. It is the reason some dark nebulae linger for ages, while others, with just a slight nudge, embark on the magnificent journey toward becoming a solar system. The collapse begins not as a uniform crunch, but as a chaotic, accelerating rush. The heart of the cloud fragment, where gravity's grip is strongest, gives way first. This central region plummets inward, a cascade of gas and dust falling toward a point that does not yet exist. As it falls, something fundamental happens. All that gravitational energy, the immense potential of a cloud falling in on itself, does not simply vanish. It transforms. The energy of motion converts into heat. The core, once colder than the void of space, begins to warm. The density skyrockets from a few thousand particles per cubic centimeter to billions, then trillions. The free fall is breathtakingly fast by cosmic standards, taking only a few tens of thousands of years for the inner region to condense by a factor of 1,000,000. But the entire cloud is not moving as one. This is where a simple inward fall becomes something far more structured. The cloud fragment, like everything in the galaxy, has a faint, inherited spin. It might be a slow rotation from the turbulent motions of its parent nebula. As the collapse proceeds, this spin becomes dramatically important due to a fundamental law of physics, the conservation of angular momentum. Think of an ice skater pulling their arms in during a spin. As their mass moves closer to their axis, they spin faster and faster. The same principle governs the dying cloud. The infalling material conserves its original, tiny bit of spin, and as it gets closer to the center, that rotation amplifies tremendously. The result is that the straightforward collapse becomes organized. Material cannot fall directly into the center anymore. Instead, it smears out, colliding and merging into a vast, flattened, rotating structure encircling the hot core. This is the birth of the protoplanetary disk, a swirling platter of gas and dust that will become the construction site for planets. At the very center of this maelstrom, the density and temperature climb to staggering levels. The core is now a seething, opaque ball of hydrogen, glowing a dull red from the heat of its own compression. This is a protostar, a stellar embryo still shrouded in its thick, infalling blanket of material. It is not yet a true star, for nuclear fusion has not ignited in its heart. That requires temperatures in the millions of degrees, a milestone still to come. For now, it is a gravitational trap, a newborn sun in waiting whose fierce warmth begins to push back against the chaos that formed it. The system has taken its first definitive shape, a central gravity well with a spinning disk of potential, setting the stage for the next, even more delicate phase of construction. Within this swirling chaos, a new order emerges. The protoplanetary disk is not a formless cloud, it is a cosmic carousel, a vast, flattened structure spinning around the newborn protostar. All the material that could not fall directly into the star's embrace has been organized by that inherited spin into this thin, rotating platter of gas and dust. This is the ultimate construction zone, the factory floor where planets will be assembled. For the first time, those microscopic dust grains are no longer adrift in a random sea. They are locked into precise, stable orbits, like countless tiny satellites all circling in the same plane around their central sun. This orderly motion is the prerequisite for everything that follows. Without this disk, the dust would simply continue to spiral inward and be consumed, leaving nothing behind to build worlds. The disk provides a safe, stable environment where particles can meet, collide, and stick together, beginning the long journey from microscopic speck to planetary body. The conditions within this disk are not uniform. They follow a strict and fateful gradient dictated by the young star's fierce heat. Imagine standing at the center, near the protostar itself. The radiation here is intense, a blistering wind of energy. Temperatures soar to thousands of degrees, enough to vaporize almost any solid material. In this inner region, close to the furnace, only the most refractory substances can survive as solids. Silicate minerals and metals, the tough dust grains forged in supernova, remain. Everything else, including water and other volatile compounds, exists only as gas. This scorching zone will one day become the realm of the rocky planets. Now take a step outward, moving farther from the star's heat. The temperature drops steadily. At a critical distance known as the frost line or snow line, it becomes cold enough for volatile molecules to condense directly from gas into solid ice grains. Water, ammonia, methane, and carbon dioxide freeze onto the surfaces of dust particles, creating icy mantles. Beyond this line, the building materials become far more abundant. Not only do you have the original rocky and metallic dust, but you now have vast reserves of ice as well. This outer region, cold and rich, will become the domain of the gas giants and icy worlds. The temperature gradient of the disk, therefore, acts as a cosmic zoning ordinance. It predetermines the basic ingredients available at different distances from the star, which in turn dictates the fundamental nature of the planets that will form there. A world born inside the frost line will be built primarily from rock and metal, dense and solid. A world born outside it will have a rocky core, but can also accumulate massive amounts of gas and ice, growing to enormous sizes. This simple rule of heat and distance, established in the disk's earliest days, writes the blueprint for the entire future solar system. What does it mean that Earth's rocky composition was decided by our distance from a still-forming sun? It means our world's very essence was shaped by its address in a swirling cloud of dust, a receipt written in heat and ice. Within the calm mid-plane of this spinning disk, a quiet revolution begins. Far from the turbulent inflow near the protostar, the central region of the disk becomes a zone of relative peace. Here, the microscopic dust grains, the legacy of ancient stars, are no longer simply passengers. They become active participants in their own destiny, embarking on the first fragile steps toward becoming a world. This process starts with a gentle sinking. The disk's own gravity, weak but persistent, pulls these tiny particles downward toward the thinnest central plane of the carousel. It is a slow, patient settling, like fine snow drifting to the ground on a windless day. Over thousands of years, the mid-plane becomes a dense, dusty fog, a concentrated layer where encounters between grains become not just possible but inevitable. But how do these specks, each 1,000 times smaller than a grain of sand, ever manage to stick together? The forces at play here are incredibly subtle. One is the constant, random jostling of the gas molecules around them, a phenomenon called Brownian motion. This keeps the dust grains gently vibrating and moving, ensuring they occasionally bump into one another. More importantly, the grains do not all orbit at exactly the same speed. Slightly larger grains feel a different drag from the surrounding gas than smaller ones, causing them to drift at different velocities. This differential drift means grains are constantly overtaking one another, leading to gentle, glancing collisions. When they touch, something remarkable happens at the atomic level. The molecules on their surfaces exert a faint, attractive force on each other. This is the van der Waals force, a weak electrical attraction that acts like a temporary, sticky glue. It is not strong enough to bind large rocks, but for these microscopic particles, it is more than sufficient. When they drift close enough, they stick. One grain meets another, and they form a tiny, fragile cluster. That cluster then bumps into a third and a fourth. This slow, persistent gathering is called coagulation. It is not a violent crash, but a delicate dance of accumulation. The resulting structures are not solid pebbles, but extremely porous fractal aggregates, often compared to cosmic dust bunnies or delicate snowflakes. They are mostly empty space held together by the faintest of forces. Yet this is the monumental first step. From isolated, invisible specks, these grains have begun to build something larger. They have crossed the threshold from passive material to active construction, creating the first seeds from which, against all odds, mountains and worlds will eventually grow. What does it mean that the foundation of every planet relies on such weak, atomic-scale stickiness? It means the universe builds its greatest structures not with force, but with patience and the gentlest of touches. But this delicate dance of accumulation faces a sudden and catastrophic crisis. As those porous dust aggregates gently collide and merge, they slowly grow, reaching sizes of pebbles, then cobbles, and eventually approaching the scale of a boulder, roughly 1 meter in diameter. This is the meter-size barrier, a notorious and seemingly insurmountable wall in the theory of planet formation. It is a point where the very physics that helped the grains come together now turns violently against them. The problem is the gas. While the disk provides a stable environment, it is not empty. It is filled with a thin but significant atmosphere of hydrogen and helium, and this gas creates a powerful headwind for any object moving through it. For microscopic grains, this drag is negligible. For kilometer-sized asteroids, it is almost irrelevant, but for meter-sized boulders, it is perfectly tuned for disaster. These objects are large enough to feel significant drag from the gas, yet too small to have enough inertia to simply plow through it. The result is a devastating loss of orbital energy. As a meter-sized boulder orbits the young star, it is constantly plowing into this gaseous headwind. With every revolution, it slows down just a little. And in orbital mechanics, if you slow down, you cannot maintain your altitude. You begin to fall. Calculations show the effect is shockingly fast. A 1-meter object in the region of Earth's future orbit could spiral inward from that distance all the way into the blazing furnace of the protostar in a mere 100 years. This timescale is a cosmic blink of an eye, far too short for the boulder to have any chance of growing further through slow collisions. The meter-size barrier presents a brutal paradox. The growth process seems to naturally produce objects of this size, yet the laws of physics appear to mandate their swift and total destruction. If this barrier is absolute, then planet formation grinds to a halt almost before it begins. Every potential planetesimal, every building block of a world, would be doomed to a fiery demise long before it could become a true planetary embryo. This is not a minor hiccup in the theory, it is a fundamental showstopper. For decades, this puzzle haunted astronomers. How could the universe possibly build planets if the most logical path led directly into the stellar furnace? The answer would require looking beyond simple, gradual growth and into the hidden, turbulent structures within the disk itself. The meter-size barrier seemed to present an absolute dead end, a cosmic filter that doomed every potential building block. But nature is rarely so simple, and astronomers refused to accept a universe that could not build planets. They began to look for loopholes in the physics, for hidden pathways that could shepherd these fragile boulders past the point of destruction. The leading theories today suggest the disk itself, in its turbulent complexity, provides the escape route. One compelling idea focuses on the behavior of the gas. A protoplanetary disk is not a smooth, placid river. It is filled with swirling eddies and turbulent vortices like whirlpools in a flowing stream. These eddies can act as natural traps. Within them, pressure differences can cause solid particles to drift toward the calm centers, concentrating pebbles and boulders into incredibly dense, confined regions. This process, called turbulent concentration, is like a cosmic gathering. Instead of individual boulders fighting the headwind alone, they are swept together into a crowded swarm. In these dense clumps, collisions are not just likely, they are constant. The meter-size objects are no longer isolated targets for gas drag. They are packed so tightly that they can rapidly merge, gluing together through gentle impacts or even sticking due to their own weak gravity, quickly jumping from the dangerous meter scale to the safer kilometer scale in the protective heart of a vortex. But perhaps an even more elegant solution lies in a subtle dance between the solids and the gas itself, a process known as the streaming instability. This theory turns the problem on its head. It proposes that the solid particles are not just passive victims of the gas flow, they can actively reshape it. As boulders and pebbles orbit, they drag on the surrounding gas slightly, creating a feedback loop. In regions where solids are slightly more concentrated, they drag the gas along with them more effectively, making it orbit a bit faster. This actually reduces the headwind they feel. This reduction in drag allows more solids to drift into the region, further amplifying the effect. It is a self-reinforcing cycle. The particles perturb the gas, which in turn herds more particles together. This can lead to runaway concentrations where the density of solid materials spikes by a factor of 100 or 1,000 compared to the surrounding disk. When these clumps become dense enough, their collective gravity becomes the dominant force. They are no longer just a loose collection of rocks, they are a gravitationally bound cloud of debris. And in a final, decisive step, this cloud undergoes a rapid gravitational collapse, not over millions of years, but in a matter of orbits. It directly forms a solid object tens or even hundreds of kilometers across, a fully formed planetesimal, in one swift event. This leapfrogs the entire meter-size barrier altogether. The building blocks of planets are not painstakingly glued together pebble by pebble. They are born wholesale from the gravitational collapse of dense particle swarms. These two ideas, turbulent concentration and the streaming instability, represent the frontier of our understanding. They are not yet settled fact, but the leading frameworks in a vibrant field of research, tested against sophisticated computer simulations and the growing census of exoplanetary systems. They offer a thrilling vision, a universe where chaos and feedback create order, where planets find a way to be born against all odds. What does it mean that the very instability that threatened to destroy planetary seeds might be the engine that builds them? It suggests a universe of profound connection where problems contain their own beautiful, hidden solutions. Once past the treacherous meter-size barrier, a new class of celestial object emerges from the chaos. These are the Planetesimals, the first true planet builders, ranging from a modest kilometer across to the size of small countries, hundreds of kilometers in diameter. These are no longer loose collections of dust or fragile swarms. They are gravitationally bound, solid bodies. Their own gravity, however faint, now becomes a defining force. It is strong enough to pull their material into a roughly spherical shape, smoothing out the irregular, fractal aggregates of their birth. More importantly, it allows them to hold onto their identity. They are persistent. They do not spiral into the star on a short timescale, nor are they easily shattered by every collision. They become permanent residents of the swirling disk, enduring for millions of years. This marks a fundamental transition in the young solar system. The protoplanetary disk is no longer just a smooth blend of gas and microscopic dust. It is now a disk populated with countless solid worlds in miniature, each a potential seed for something far greater. They are the foundational stones upon which the architecture of planets will be raised. What does it mean that our Earth was once a member of this vast swarm of primordial planetesimals? It means our world's deepest history is written in the gentle, persistent pull of its own first gravity. With their own gravity now at play, these countless planetesimals begin a slow but relentless game of cosmic capture. The rules of this game are brutally simple, and they favor the biggest players from the very start. This next phase is called Runaway Accretion, and it is driven by a principle known as gravitational focusing. Imagine two planetesimals on similar orbits. The smaller one is like a tiny marble, the larger one is a massive boulder. As they drift through space, their gravitational fields reach out invisibly. The larger body, with its stronger gravity, acts like a wider net. It does not just occupy its own physical space, it bends the paths of nearby objects toward it. When a smaller planetesimal passes by, it is not just aiming at the large body's physical cross-section. It is aiming at a much larger gravitational cross-section, a target area amplified by the pull of gravity itself. This makes collisions far more likely than if they were just randomly bumping together. Every successful collision adds more mass to the larger body, which in turn increases its gravity, which then makes its cross-section even larger, attracting even more material. It is a self-reinforcing cycle of growth, a positive feedback loop where the rich get richer at an accelerating pace. In the orbital zone where Earth would one day form, a handful of lucky planetesimals, perhaps just 1 in 1,000, get an early lead. They begin to snowball, growing from hundreds of kilometers across to the size of small moons, then to the scale of Mercury or Mars, all while their smaller neighbors are steadily consumed. This runaway phase does not last forever, however. As these leading bodies grow into true protoplanets or planetary embryos, they begin to dominate their immediate surroundings. Each one carves out a wide swath of the disk, a zone of influence called its feeding lane. Through their gravitational pull, they either sweep up the remaining planetesimals within that lane or violently scatter them away, sometimes ejecting them from the solar system entirely. This process of clearing their neighborhood marks the transition to a new, more orderly and competitive stage, oligarchic accretion. The word oligarch comes from the idea of rule by a few. In the inner solar system, the dozens of runaway winners have now become the oligarchs. They are spaced apart at roughly similar distances, each having cleared its own orbital territory. Their growth slows from the frantic pace of runaway accretion to a steadier, more regulated competition. They can no longer easily reach across the gaps to consume one another, so they focus on mopping up the last remnants of debris within their own zones. The result, after perhaps 10 million years of this process, is a dramatic new landscape. The primordial swarm of countless planetesimals is gone. In its place, orbiting the young sun, are a few dozen substantial worlds. In the region from the future orbit of Mercury out to the asteroid belt, we would find perhaps 20 to 30 of these planetary embryos, each one a formidable body. Some are the size of the Moon, many are as large as Mars, and a few of the most successful might already approach the mass of Earth. They are not the planets we know today, but their direct giant progenitors. They are hot, molten worlds from the energy of countless impacts, possibly even possessing thin, temporary atmospheres of vaporized rock. The disk is no longer a smooth blend, but a sparsely populated arena where these few massive players circle the Sun, waiting for the final, most chaotic act of planetary construction to begin. What does it mean that Earth was once not alone, but one of many sibling worlds of similar size? It means our planet's birth was not a solitary event, but a crowded, violent competition for material in the early solar system. Yet this fierce competition among the inner embryos was only one part of the story. The architecture of the entire solar system was being dictated by a single, invisible boundary, a frontier of cold that would determine the fate of worlds. This is the snow line, also called the frost line, and it is one of the most important concepts in planet formation. It is not a physical wall, but a radial distance from the young star where the temperature in the protoplanetary disk drops below a critical point, around 170 degrees Celsius below zero. At this frigid threshold, a magical transformation occurs. Volatile compounds, which had existed only as gas in the hotter inner disk, can now condense directly into solid ice grains. Water is the most abundant and important of these volatiles, but the freeze also includes molecules like ammonia and methane. Think of it as a cosmic dew point where the breath of the disk crystallizes into frost. The consequences of crossing this line are staggering. Inside the snow line, the only solid building materials are the tough, refractory dust grains, the silicates and metals that can withstand the star's heat. Beyond it, those same rocky grains become coated in thick icy mantles, and trillions of additional pure ice particles join the mix. The inventory of solid material doesn't just increase, it explodes. Astronomers estimate that beyond the snow line, the amount of solid mass available for planet building can be 4 to 10 times greater than in the inner disk. It is the difference between trying to build a castle with only bricks and having an unlimited supply of bricks, mortar, and timber. This abundance changes everything for the planetesimals forming there. With so much more solid stuff to sweep up, their runaway growth is supercharged. They can accrete material faster and grow to become true giants, not just planetary embryos, but planetary cores of immense scale, reaching 10, 15, even 20 times the mass of Earth in a relatively short time. This is the decisive advantage. A core that massive develops a gravitational pull so powerful that it can no longer just collect ice and rock. It begins to do something extraordinary. It starts capturing the disk's primary component, the vast ocean of hydrogen and helium gas that had, until now, simply swirled around it. This is the birth of a gas giant. The snow line, therefore, writes the fundamental blueprint for every solar system. It creates a clear zoning ordinance, hot and dry on the inside for small, rocky worlds, cold and rich on the outside for giant, gassy planets. In our own solar system, the snow line sat somewhere between the present orbits of Mars and Jupiter. Inside it, the rocky embryos competed for scarce material, leading to the 4 terrestrial planets we know. Just beyond it, however, where solid mass was plentiful, 1 or 2 lucky cores grew fast enough to become the seeds of Jupiter and Saturn, forever altering the destiny of everything else. What does it mean that the giant planets are, at their hearts, massive snowballs forged from ice and rock? It means the architecture of our cosmic neighborhood was frozen into place before the sun had even finished forming. This immense core, forged from ice and rock beyond the snow line, now holds the key to a planetary metamorphosis. It has reached a critical threshold, roughly 10 times the mass of Earth, a milestone that triggers a new and dramatic phase called core accretion. Up until this point, the growing protoplanet had been gathering mostly solid material. the planetesimals and icy chunks within its gravitational reach. But once its core crosses that 10 Earth mass line, its relationship with the surrounding disk changes forever. Its gravity becomes so powerful that it can no longer ignore the primary component of the nursery, the vast sea of hydrogen and helium gas. This gas had been orbiting the Sun as a smooth background, but now the core's gravity begins to pull at it, creating a deep well in the fabric of the disk itself. At first, the gas slowly accumulates around the solid core, forming a thick, extended envelope. This envelope is bound by gravity but still relatively tenuous, and the planet continues to grow slowly, both by accreting more solid debris and by gradually pulling in more gas. This is the initial, steady phase of gas accretion, a patient gathering that can last for hundreds of thousands of years. But then, something flips a switch. The growing envelope reaches a point of no return in its own mass. Its own self-gravity becomes significant, and it begins to collapse inward under its own weight, pulling even more gas from the disk down onto the core at a ferocious rate. This is runaway gas accretion, and it is one of the most explosive events in planetary formation. Though it happens in the eerie silence of space, the planet becomes a voracious vacuum cleaner for the disk's gas. In a staggeringly short time, perhaps only 10,000 years, the vast majority of the planet's final mass is acquired. A world that was once a super-Earth-sized ball of ice and rock swells into a true colossus, a gas giant like Jupiter or Saturn. The planet's atmosphere becomes deep and massive, compressing under incredible pressures until hydrogen, the simplest element, behaves in exotic ways, becoming a metallic fluid deep within. This runaway feast does not go unnoticed by the rest of the solar system. The newborn gas giant is a gravitational titan, and its presence sends powerful ripples through the remaining disk. Its gravity carves a gap, a cleared lane in the gas along its orbit, like a giant plow creating a furrow in a field. It also begins to shepherd and scatter remaining planetesimals, hurling some inward toward the star and others outward into the dark, in a gravitational reshuffling that will define the final architecture of the entire planetary system. The birth of a gas giant is not a quiet local event. It is a galactic-scale announcement that forever changes the neighborhood. What does it mean that Jupiter's explosive growth likely hurled the building blocks of water and life toward the inner solar system? It suggests the giant planets are not just distant spectators but active architects of our own existence. Yet the story of how a gas giant is born may not have just one author. While core accretion is the leading narrative, a compelling alternative script exists, one that rewrites the very first act. This is the theory of gravitational disk instability, and it proposes a shortcut of staggering speed. Imagine if the swirling protoplanetary disk did not need to patiently build a massive core first. Instead, what if under the right conditions, the disk itself could spontaneously break apart, directly giving birth to giant planets in a single, swift event? The requirements for this are specific and extreme. The disk must be exceptionally massive, containing a large fraction of the young star's own mass. It must also be able to cool very rapidly, losing the internal heat that would otherwise keep it stable. When these two conditions align, something remarkable can happen. The disk's own self-gravity, the collective pull of all that gas and dust, can overcome the internal pressure and rotational forces trying to hold it together. It becomes gravitationally unstable, like a spinning rope of water breaking into droplets, or a smooth cloud of smoke curling into distinct vortices. The disk can fragment. It develops spiral arms of enhanced density that then pinch off into individual, bound clumps. Each of these clumps is not a solid core with a growing gas envelope, but a self-contained ball of primarily hydrogen and helium gas from the very beginning. This clump, if it survives, would then contract under its own gravity, potentially drawing in solid material to form a core later. or perhaps remaining a mostly gaseous world without a substantial solid heart. The timescale here is the most dramatic difference. While core accretion requires millions of years of patient assembly, disk instability can form a giant planet in a mere 1,000 years, a blink of an eye on the cosmic clock. This theory offers a potential explanation for some of the most puzzling planets we have discovered orbiting other stars. How do we explain gas giants found orbiting incredibly far from their host stars, in regions where the disk material would have been too sparse for core accretion to work in the system's short lifetime? How do we account for the most massive planets, several times the size of Jupiter? Disk instability provides a possible pathway. It suggests that in the most massive, turbulent disks, planets could form quickly at great distances or grow to tremendous sizes directly from the disk's raw material. The existence of this competing theory does not mean core accretion is wrong. In fact, most astronomers believe it is the primary method for forming planets like Jupiter and Saturn in our own solar system. Instead, it highlights a thrilling reality. The journey from microscopic dust to a giant world is not a single, settled story. It is a menu of cosmic possibilities. Our solar system may have followed the slow core accretion path, while another, more massive disk in a different part of the galaxy may have taken the fast track of instability. This duality reminds us that planet formation is not a rigid assembly line, but a dynamic and creative process where the initial conditions of mass, temperature, and chaos write unique destinies for every family of worlds. What does it mean that nature may have two completely different recipes for building a giant planet? It suggests the universe is a more inventive and varied architect than we ever imagined. But how can we possibly know any of this? We are talking about events that happened over 4.5 billion years ago, in Nurseries light years away. The answer lies in turning our gaze not just to the stars, but to the faint, cold glow of the dust itself. For modern astronomers, these microscopic grains are not just the ingredients of planets, they are a powerful diagnostic tool, a way to observe the invisible processes of cosmic construction in real time. We cannot watch a single planet form over millions of years, but we can study thousands of young stars, each frozen at a different moment in its developmental timeline. By observing the dust around them, we piece together the movie of solar system birth, frame by frame. The key is that dust, no matter how cold, emits its own light, not in the visible spectrum we see, but in the longer wavelengths of infrared and radio light. A warm dust grain, heated by a young star, glows brightly in the infrared. This is how space telescopes like the Spitzer Space Telescope and the James Webb Space Telescope have revolutionized our view. They peer through the obscuring veils of gas to map the detailed structure of the inner, hotter regions of protoplanetary disks, revealing spirals, rings, and cavities sculpted by newborn planets. For the colder, outer regions of the disk, where ices dominate and giant planets may be forming, we need to look at even longer wavelengths in the millimeter and submillimeter range. Enormous radio telescope arrays like the Atacama Large Millimeter Array, or ALMA, high in the Chilean desert, are exquisitely tuned for this task. They detect the faint thermal whisper of dust grains only a few tens of degrees above absolute zero. ALMA does not see a smooth, featureless disk. Instead, it reveals stunning, high-resolution portraits of concentric rings and dark gaps, like the grooves on a cosmic record. These gaps are the telltale signatures of unseen planets. As a young planet orbits, its gravity acts like a cosmic plow, clearing a path in the dust and gas, creating a lane of emptiness that our telescopes can detect as a dark band. By analyzing the specific wavelengths of light emitted, scientists can even determine the composition of that distant dust, identifying the chemical fingerprints of silicates, carbon compounds, and water ice. Each observation is a snapshot, a clue in a vast interstellar detective story. We are not just looking at pretty pictures, We are reading the blueprints of solar systems under construction, watching the very architecture of alien worlds being drafted in light and shadow. What does it mean that we can witness the birth of planets around other stars? It means the story of our own origins is no longer a theoretical mystery, but a visible, ongoing process written across the galaxy. These glowing portraits of distant disks are not just beautiful, they are a forensic record. The intricate structures they reveal, the gaps and the spirals, are the direct signatures of unseen worlds in the act of carving out their domain. This is how we catch planet formation in the act, by reading the disturbances left in the dust. The most definitive signature is a gap. Think of a massive satellite orbiting within a vast, thin ring of debris. As it travels, its gravity exerts a repeated, rhythmic tug on every speck of dust and pebble along its orbital path. Over time, this gravitational influence acts like a cosmic snowplow. It either ejects the material from that specific lane, pushes it inward or outward, or gathers it up directly through accretion. The result is a cleared corridor, a dark band of relative emptiness encircling the star, set between bright rings of dust that have been piled up at the gap's edges. For astronomers, a clean, dark gap in a millimeter wave image from an instrument like ALMA is as close to a smoking gun as you can get. It strongly suggests the presence of an embedded protoplanet, likely already a gas giant, actively shaping its environment. The width and depth of the gap even give clues about the planet's mass and age, but planets, especially younger, smaller ones, can leave other, more subtle fingerprints. A world still growing within a gas-rich disk does not just interact with the dust, it also perturbs the surrounding sea of hydrogen and helium. As the planet orbits, its gravity can excite waves in this gas, much like a boat moving through water creates a wake. In the unique physics of a rotating disk, these disturbances can coalesce into grand, sweeping spiral arms. These are not solid structures, but spiral density waves, regions where the gas is slightly compressed, which in turn drags and concentrates dust particles into these brilliant, swirling patterns. A single massive planet can often generate two distinct spirals, one winding inward ahead of its orbit and one trailing outward behind it. These dramatic features, seen in near-infrared light where warmer dust glows, are the whirlpools and eddies of planet formation, the visible turbulence created by a hidden anchor stirring the cosmic waters. So when we look at an image of a young star system and see a series of dark, concentric rings or a pair of elegant, bright spirals, we are not just looking at abstract art. We are reading a real-time construction update. We are seeing the gravitational signature of infant planets, the indirect but powerful evidence that right now, around that faraway star, the chaotic dance of dust is giving way to the orderly architecture of a new solar system. What does it mean that a gap in a ring of dust is proof of a new world? It means the universe announces its creations not with a bang, but with a silent, geometric signature written in ancient starlight. The most profound evidence of our cosmic origins is not found in distant telescopes, but locked within ancient rocks that fall to Earth. Primitive meteorites, the unaltered leftovers from the solar system's construction site, contain microscopic time capsules called Presolar grains. These are not just old, they are older than the sun itself. They are literal stardust, tiny mineral fragments that formed around other stars in other eras, and were later incorporated into the cloud that birthed our own solar system. Finding them is a monumental task, requiring scientists to dissolve meteorites in strong acids, destroying over 99% of the rock to isolate the few, incredibly resilient grains that remain. What survives are the toughest minerals like silicon carbide, graphite, and nanodiamonds, each grain smaller than the width of a human hair. Their true story is written not in their shape, but in their atomic hearts, in the specific fingerprints of their isotopes. Isotopes are versions of an element with different numbers of neutrons in their nuclei. The ratios of these isotopes are like a cosmic barcode, imprinted by the unique nuclear furnace in which the atom was forged. When researchers analyze these presolar grains with instruments called mass spectrometers, they find isotopic signatures that are wildly exotic, completely unlike anything formed in our solar system. A grain might have an overabundance of certain isotopes of oxygen, or neon, or silicon, that could only have been produced under the extreme, specific conditions inside a dying star. By reading this atomic barcode, astronomers can trace individual dust grains back to their stellar nurseries. Some grains, rich in specific heavy elements, carry the unmistakable signature of a Type II supernova, the explosive death of a massive star. Others, with different isotopic patterns, point to the more gentle, windy outflows of aging red giant stars. It is a form of celestial archaeology. Each microscopic speck is a relic with a documented provenance, a piece of debris from a specific stellar event that occurred billions of years ago, long before our sun was a glimmer in a collapsing cloud. This means the dust that seeded our solar system was not a uniform paste, but a rich amalgam of heritage materials, a cosmic inheritance from a diverse population of ancestral stars. What does it mean that your body contains atoms forged in those same ancient stellar explosions? It means you are, in the most literal sense, made of stardust with a traceable lineage. Not every planetesimal was destined to join a growing world. For every winner in the gravitational competition, there were countless others left behind, frozen in time. These are the leftovers, the survivors of the solar system's violent youth, and they form two distinct families of cosmic wanderers. Their nature depends entirely on where they were born in that ancient, swirling disk. Those that formed inside the frost line, in the hot, dry region where Earth and Mars grew, were built from rock and metal. They are the asteroids. They are the primordial building blocks of the rocky planets that never got swept up, preserved in the deep freeze of space. Their orbits, mostly concentrated in the vast belt between Mars and Jupiter, are a testament to the gravitational influence of the giant planet. Jupiter's immense gravity stirred this region so violently that planetesimals there could never peacefully coalesce into a single world. Instead, they remain a scattered collection of fragments, constantly jostling but rarely merging, a fossilized construction zone. Venture farther out beyond the realm of the giants, and the leftovers are of a different kind. Here, in the cold darkness past Neptune, the building material was dominated by ice. The planetesimals that formed here are the cometary nuclei, often called dirty snowballs or icy dirt balls. They are mixtures of water ice, frozen gases like carbon monoxide and methane, and embedded dust grains. This distant reservoir is the Kuiper Belt, a vast, donut-shaped region home to countless frozen relics. Some were flung even farther by gravitational encounters, forming a distant, spherical shell of icy bodies known as the Oort cloud. These icy time capsules spend most of their existence in profound stillness, but when a gravitational nudge sends one falling inward toward the sun, it transforms. The heat vaporizes its ices, creating the glorious, glowing coma and tail that make comets such spectacular visitors. Both asteroids and comets are more than just cosmic debris. They are the solar system's original filing cabinets. Locked within their structures are the unprocessed ingredients of the protoplanetary disk. A primitive carbonaceous asteroid is a compacted sample of the very dust that settled in the mid-plane, containing complex organic molecules and water-bearing minerals. A comet nucleus is a frozen chunk of the outer disk's ices, preserving the same water and volatile chemistry that existed over 4 billion years ago. By studying them, we are not looking at planets. We are handling the raw construction materials themselves, the pristine dust and ice from which everything else was made. What does it mean that these leftovers are our most direct link to the solar nebula? It means to understand our own genesis, we must study the fragments that never finished building. The final act of planetary construction was not a gentle settling but a cataclysm. The young solar system, even after the giant planets had formed, remained a chaotic shooting gallery. For hundreds of millions of years after Earth's accretion, a vast swarm of leftover planetesimals, the rocky asteroids and icy comets, still crisscrossed the orbits of the New World. This period culminated in an event known as the Late Heavy Bombardment, a spike of intense impacts that scarred every solid surface in the inner solar system. The evidence is written on the face of our moon in its ancient cratered highlands. Those circular basins are not random blemishes, they are the timestamp of a cosmic storm, a time when space was filled with flying debris. For the newly formed Earth, this was a time of unimaginable violence. The sky would have been constantly lit by the brilliant streaks of incoming objects, followed by titanic explosions that vaporized rock, melted the crust, and churned the young planet's surface into a global ocean of magma. It was an epoch of seemingly pure destruction, a hellish environment where any fragile beginnings of chemistry would have been sterilized over and over again. Yet within this apocalyptic fury, a profound paradox unfolded. The very objects that brought devastation also carried the essential gifts for life. Those icy comets, hurled inward from the distant Kuiper belt and Oort cloud by the gravitational nudges of Jupiter and Saturn, were not just balls of dirty ice. They were cosmic delivery vehicles packed with the precious volatiles that the hot, inner solar system had lacked. With every colossal impact, a comet would disintegrate, releasing vast quantities of water vapor into the primitive atmosphere. Over millions of years, as the planet cooled, this vapor condensed and fell as rain, filling the basins to create the first oceans. But water was only part of the delivery. The asteroids and comets themselves were made from that original, complex cosmic dust. This dust, remember, contained carbonaceous compounds, the same organic molecules forged in interstellar space and within the protoplanetary disk. These are the building blocks of life, amino acids and other prebiotic compounds. Scientists have found them preserved within primitive meteorites that fall to Earth today, proving they survived the journey from the disk to planetesimals. During the late heavy bombardment, these carbon-rich asteroids and the dusty cores of comets rained down upon the young Earth, seeding its surface and oceans with a steady influx of organic material. So this violent chapter, which once seemed like a random finale of chaos, is now understood as a potentially essential step in the recipe for a habitable world. The Earth, born hot and dry inside the frost line, was gifted its oceans and the chemical precursors for biology by the very leftovers of its own formation. The dust that began as microscopic grains around other stars, that clumped into planetesimals, and that avoided accretion into planets, finally completed its epic journey. It crashed onto a rocky world, delivering the water for its seas and the carbon for its future biology. This transforms our view of the bombardment from a mindless catastrophe into a cosmic provisioning. The chaos was not an interruption of the story, it was the concluding chapter of planetary assembly and the opening act of planetary preparation. What does it mean that the water in your glass and the carbon in your cells may have arrived on Earth during a billion-year-long meteor shower? It means the story of life is inextricably woven into the older, grander story of dust, gravity, and impact. The violent bombardment of the young planets eventually subsided, leaving behind a quieter, more stable solar system. Yet the story of cosmic dust does not end with the formation of worlds. Fast forward billions of years to mature, sun-like stars shining peacefully in the galaxy. Around many of these stars, astronomers have discovered faint, ethereal rings of dust glowing gently in the infrared. These are not the dense, gas-rich protoplanetary disks of stellar infancy. They are something else entirely, a later chapter in the life of a solar system. We call them debris disks. Brilliant, young stars like Vega and Fomalhaut are famous for their spectacular debris rings, visible as vast halos in telescope images. But our own sun has one too, a diffuse cloud of dust known as the zodiacal light, visible as a faint cone of glow in the night sky just before dawn or after sunset. This dust is fundamentally different from the primordial grains that built the planets. It is second-generation material. The original construction site has long since been cleared away. The dust we see now is not left over from the initial build, but is fresh powder, continuously generated by ongoing activity in the mature system. The source is the relentless, slow-motion demolition of the solar system's leftovers. In the asteroid belt and the Kuiper belt, leftover planetesimals still occasionally collide. When two asteroids smash together, or when a comet is slowly ground down by micrometeorite impacts, they release vast clouds of fine dust and rocky debris. This new dust then spreads out, forming a tenuous ring that is constantly replenished even as older dust spirals into the star or is blown away by stellar radiation. A bright debris disk, therefore, is not a sign of a system still under construction. It is a signpost of a planetary system with an active, bustling population of minor bodies. It tells us that planet formation succeeded, leaving behind a rich architecture of planets and a surrounding sea of asteroids and comets that are still dynamically interacting, still grinding themselves down into dust. The presence of a debris disk indicates that the chaotic processes of the early solar system have given way to a steadier, more geological timescale of erosion and collision, a mature phase where the dust is no longer a builder but a byproduct of stability. What does it mean that our solar system is still producing its own faint ring of dust? It means the great construction project is over, but the quiet maintenance and slow decay have just begun. But the story of cosmic dust is not confined to quiet nurseries like our own. This universal building material endures in the most violent neighborhoods of the galaxy, places where the very idea of a stable planet seems impossible. Consider the environment around a pulsar, the rapidly spinning, magnetized corpse of a massive star that died in a supernova. This object emits beams of intense radiation and a relentless stellar wind, bathing its surroundings in an energetic fury that should vaporize any solid material for light years. Yet, astronomers have detected faint, dusty disks orbiting some of these stellar zombies. This dust cannot be primordial, it is far too young. Instead, it is likely second generation, forged from the debris of worlds that once orbited the star before its cataclysmic death. When the star exploded, it may have torn apart its planetary system, but some of that shattered material, now a cloud of vaporized rock and metal, could have cooled and recondensed into new dust grains right in the heart of the aftermath. It is a phoenix-like cycle where destruction gives raw material for new beginnings, even in the most hostile of environments. Binary star systems add another layer of cosmic drama. When two stars orbit closely, their competing gravitational fields create a zone of chaos. A planetesimal or small planet that wanders too close to one of the stars can be caught in a tidal tug of war, literally pulled apart. The immense differential gravity stretches the object until it fractures, creating a temporary, dusty debris ring around the star, a ghostly shroud of what was once a solid world. This process, tidal disruption, shows that dust production is not always a slow grind of collisions. It can also be a sudden, catastrophic event, a stellar system cannibalizing its own children. Perhaps the most extreme testament to the resilience of dust lies at the very center of our galaxy, in the oppressive grip of the supermassive black hole known as Sagittarius, a star. The region around it is a maelstrom of powerful magnetic fields, intense X-ray radiation, and titanic gravitational forces that should tear molecules apart. Yet, infrared observations have revealed a surprising sight, a faint, dusty torus or donut-shaped structure orbiting at a precarious distance. This dust likely comes from stars that venture too close and are shredded by tidal forces, or from the dense winds of massive stars in the crowded galactic core. That any solid material can persist, can find a temporary equilibrium in such an environment, is astonishing. It means the cosmic dust cycle, from stellar death to grain formation to eventual accretion or destruction, operates on every scale, from the quiet outskirts of a solar system to the violent heart of a galaxy. This dust is not a fragile bystander. It is a persistent participant in the cosmos, a witness to both creation and annihilation, reminding us that the ingredients for worlds are everywhere, waiting for their moment in the chaos. This grand journey reveals a profound truth, a cycle without beginning or end. Cosmic dust is the ultimate recyclable material in the universe, moving through a loop of death and rebirth that connects every star, every planet, and every one of us. The cycle begins, ironically, with an ending. Inside the furious hearts of aging, massive stars, atoms are fused together, creating the heavier elements that will become the ingredients for solid worlds. When these stars reach their final moments, they do not fade quietly. In the immense outflows of red giants and the catastrophic explosions of supernova, these newly forged elements are blasted into the void. This is the moment of creation for the most complex dust grains. Silicon, carbon, iron, and oxygen are ejected in vast clouds of stellar ash, where they rapidly cool and condense into microscopic solid particles. This enriched material, now carrying the legacy of that dead star, mixes with the primordial hydrogen and helium of the interstellar medium. It becomes part of the galaxy's raw inventory. For millions of years, these dust grains drift through the silent darkness between stars, solitary travelers carrying their atomic heritage. But gravity is a patient gatherer. Over immense timescales, it draws this scattered material together, along with vast amounts of gas, into those dark, cold molecular clouds we call stellar nurseries. Here in the quiet chill, the dust waits. When a shock wave from a distant supernova or a galactic spiral arm triggers collapse, the cycle turns. The dust, along with the gas, begins its million-year fall inward. It becomes part of a protostellar disk, the seeds for new planets, and the material that will form a new star at the center. The iron in your blood, the calcium in your bones, the silicon in the rocks beneath your feet, every atom in your body heavier than hydrogen or helium was once forged in the heart of a star that no longer exists. That star lived and died, perhaps billions of years before our sun was born, scattering its enriched remains into the galaxy. Those remains became the dust that seeded our solar system. We are not just figuratively, but literally made of stardust. Your very existence is the universe's way of taking ancient stellar material and arranging it into a form that can, for a moment, look back and wonder at its own origins. This transforms our understanding of place. We are not separate from the cosmos. We are a temporary configuration of its most ancient ingredients. The oxygen you breathe was likely forged in 2 different stellar generations before finding its way to Earth. The gold in a ring or a circuit board was almost certainly created in the violent merger of 2 neutron stars, a cataclysm of unimaginable scale, with the resulting dust eventually finding its way into the nebula that birthed us. This is the ultimate cosmic loop. Stellar death feeds stellar birth. The destruction of one solar system provides the seeds for countless more. It is a cycle of perpetual renewal where the end of one story is literally the beginning of another. We are not just living in the universe, we are the universe experiencing itself. The dust has come full circle, and in doing so, it has created a creature that can trace the path of its own atomic ancestry back to the stars. What does it mean to know you are a way for the cosmos to know itself? It means the story of the dust is ultimately our own story. This grand cosmic cycle presents us with a beautiful, unified story, but it also conceals a troubling contradiction. If building a planet is such a slow, step-by-step process of gentle accumulation, then why does the universe seem to be in such a hurry? The evidence from young stars tells a clear and challenging tale. We can observe protoplanetary disks around infant suns, and what we see is a startlingly brief window of opportunity. These brilliant, swirling construction sites do not last for hundreds of millions of years. They persist for only a few million years at most before the young star's fierce radiation and powerful winds blow the remaining gas away into interstellar space. Once that gas is gone, the primary phase of planet building is over. The clock is always ticking. This creates a profound dilemma known as the efficiency problem. Can the slow, patient dance of dust grains, planetesimals, and planetary embryos possibly finish its work in such a short amount of time? For the rocky worlds like Earth, the timescale is tight but perhaps manageable. The real crisis emerges when we consider the gas giants. According to the traditional core accretion model, forming a world like Jupiter is a two-stage marathon. First, you must patiently build a massive solid core of rock and ice, at least 10 times the mass of Earth. This alone requires sweeping up countless planetesimals across a vast orbital distance, a process that models suggest could take several million years on its own. Only then can the second stage begin, the runaway accretion of gas. But if the gas disk only lasts for 3 million years, the core has to form impossibly fast to have any time left to claim its gigantic atmosphere. Otherwise, the gas is gone, and you are left with a lonely, oversized core, a failed giant. This timing problem forces astronomers to confront a critical question. Are our models too slow, or is nature much faster and more clever than we assumed? The hunt for solutions is driving some of the most exciting research in planetary science today. One leading idea completely reimagines the growth phase. It is called pebble accretion, and it proposes that planetesimals and planetary embryos do not grow solely by colliding with other objects of similar size. Instead, they feast on a constant rain of much smaller particles, pebbles ranging from millimeter to centimeter in size. These pebbles are everywhere in the disk, and they behave differently than large rocks. As they orbit, they experience a strong drag from the gas, causing them to drift slowly inward toward the star. A growing planetary core, with its significant gravity, can act like a net stretched across a river. As the stream of pebbles flows inward, the core can efficiently capture them, pulling them out of the flow and adding them to its mass. This process is far more efficient than waiting for rare collisions with other large bodies. It allows a core to grow to the critical 10 Earth mass threshold in just a few 100,000 years, well within the disk's lifetime, solving the gas giant timing problem elegantly. But pebble accretion is not the only proposed shortcut. Other researchers are investigating more dynamic and turbulent disk models. Perhaps the early disk was not smooth and uniform, but filled with large-scale instabilities and pressure bumps that acted as cosmic traffic jams, concentrating pebbles and boulders into dense rings almost instantly. These overcrowded rings could then rapidly coalesce into planetary cores through gravitational collapse, skipping the slow growth stages altogether. The efficiency problem, therefore, is not a flaw in our story, but its most vital catalyst. It pushes us to look deeper, to find the hidden physics that accelerates nature's construction. It reminds us that the serene disks we see in telescope images are likely sites of frantic, ingenious activity, where the universe employs every trick of gravity and dynamics to build worlds against a relentless deadline. What does it mean that planet formation might be a race against the dispersal of a gas cloud? It suggests that solar systems are not guaranteed, but are timely masterpieces, completed just before the workshop itself vanishes. The search for another Earth is not a hunt for a single, finished world. It is a forensic investigation into the conditions of its birth, and the most vital clues lie in the dust. By understanding how microscopic grains orchestrate the construction of solar systems, we are learning to read the blueprints of alien architectures, predicting where and when rocky, Earth-like planets are most likely to emerge. The patterns we see in distant disks are not just beautiful, they are predictive. A series of clean, dark gaps in a young disk revealed by radio telescopes tells us that multiple planets have already formed and are clearing their orbits. The specific distances of those gaps from the star, combined with the temperature profile of the disk, allow astronomers to estimate the potential sizes and compositions of those unseen worlds. Is a gap located inside the theoretical frost line, then the planet carving it is likely built from rock and metal, a terrestrial world in the making. Is the gap far outside in the cold, icy reaches, then the hidden planet is probably a gas giant or an ice giant. This dust-based detective work transforms a snapshot into a forecast. We are not just seeing what is there now, we are predicting the final planetary system that will remain long after the gas has blown away. The composition of the dust itself is another powerful guide. Using spectroscopy, scientists can analyze the faint light from a disk to determine its chemical makeup. Does the inner region show a strong signature of silicates and other refractory minerals, but a clear absence of water ice? This is the fingerprint of a hot, dry zone where rocky planets will form. Does the signal change dramatically at a certain distance, with water ice and organic molecules becoming abundant? That marks the snowline, the factory for giant planetary cores. By mapping these compositional gradients in a disk, we can essentially draw a predicted map of the future solar system, labeling zones as likely homes for Mercury's, Earth's, or Jupiter's. This is how cosmic dust acts as a tracer, revealing the invisible zoning laws that will dictate a planet's destiny long before it is fully formed. Ultimately, this knowledge refines our search for habitable worlds. If we want to find an Earth analog, we must look for stars that are the right age, where the protoplanetary disk has had enough time to form terrestrial planets, but not so much time that the system has become dynamically unstable. We must look for evidence that a rocky planet formed within that star's habitable zone, the orbital distance where liquid water could exist on a surface. And now, by studying dust, we have a new criterion. We should prioritize searching around stars whose infant disks show the right patterns, the telltale signs of efficient rocky planet formation inside the frost line. A system with a pronounced gap in its warm, inner dust ring is a prime candidate for hosting a completed terrestrial world. The study of cosmic dust, therefore, elevates exoplanet science from a game of chance to a strategic search. We are learning to listen to the whispers of the construction site, to understand the plans before the building is even finished. This means the dream of finding another pale blue dot begins not with a telescope pointed at a planet, but with one pointed at the faint, glowing dust that will one day become it. Yet the most profound revelations about our dusty origins are still on the horizon. The next generation of astronomical observatories, now being built or planned, will transform these faint whispers from distant disks into a clear, detailed conversation. They are designed to answer the very questions this story has raised, testing each theory with unprecedented precision. The James Webb Space Telescope, already revolutionizing our view, is just the beginning. Its powerful infrared eyes are exquisitely tuned to detect the chemical fingerprints of complex molecules clinging to dust grains in the inner regions of disks. It can identify the specific organic compounds present, mapping the distribution of water, carbon monoxide, and even the building blocks of more complex chemistry, showing us the exact ingredients available to nascent planets in their star's habitable zone. On the ground, a new class of giant eyes is preparing to open. The extremely large telescope, under construction in the high desert of Chile, will combine a mirror nearly 40 meters across with advanced adaptive optics to cancel out the blurring effect of Earth's atmosphere. This will allow it to do something astonishing: directly image protoplanetary disks in visible and near-infrared light with stunning clarity. It will not just see gaps and spirals, it will potentially resolve the thermal glow of individual, newly formed gas giants still embedded in their dusty cradles, watching them in real time as they interact with and sculpt their birth environment. This is the next step from inference to direct observation. But the ultimate ambition lies even further ahead. Concepts for future space-based interferometers envision not a single telescope, but a fleet of them flying in precise formation, creating a virtual observatory with a mirror the size of the distance between them. Such an instrument could achieve angular resolution so fine it could, in theory, map the surface of an exoplanet or watch a dust grain drift within a disk's spiral arm. It would allow us to trace the motion of material, to see if pebbles are truly streaming inward as the pebble accretion theory predicts, or if gravitational instabilities are carving out structures directly. These tools will move us from studying snapshots to watching the movie of planet formation, frame by exquisite frame. They will test whether the streaming instability is fact, whether pebble accretion is the dominant engine for building cores, and how universal our own solar system story truly is. The dust has held its secrets for billions of years, but the light carrying those secrets is finally reaching telescopes powerful enough to understand its language. From microscopic specks in the frigid dark to the grand architecture of worlds, this is the story written in dust. It is a narrative where the smallest particles are the most powerful actors, the quiet architects of cosmic destiny. These grains are not passive space debris drifting aimlessly until gravity gives them purpose. They are active agents of change. Their faint stickiness begins the gathering. Their chemical diversity seeds the composition of planets. Their very presence cools and shapes the swirling disk, enabling gravity to craft rings and gaps that become the cradles for new worlds. Every gap in a distant protoplanetary disk, every ring of debris around an aging star, is a signature of dust's enduring influence. This journey transforms our understanding of our place in the cosmos. The iron in your blood, the silicon in the soil, the water in your glass, these are not earthly inventions. They are borrowed stardust, atoms forged in ancient stellar furnaces, carried on microscopic grains across light years, and delivered to our nascent planet during the chaotic final acts of construction. We are not just living in a universe of stars and planets, we are living in a universe of dust reassembled. So the next time you look up at the night sky, see beyond the bright points of light. See the darkness between them not as empty void, but as a fertile field, a silent ocean of potential. Within that apparent nothingness drifts the granular future of solar systems, the microscopic seeds from which every star, every planet, and every story like our own must begin.